Screaming at a cup of coffee for long enough would technically heat the liquid up. Understanding this transfer of energy requires unlearning the school analogy of a ripple in a pond. When a droplet hits a pool, it forces water downward, pushing the surrounding liquid up into a crest. This transverse wave only exists because gravity acts as a constant shear force, immediately pulling the displaced water back down into place. The empty air between us has no surface. It lacks the strong cohesive forces of a liquid or a solid that would snap displaced molecules back into a rigid alignment. Without those forces, transverse waves, motion that moves up and down perpendicular to its path, are physically impossible in the atmosphere. Acoustic energy travels as an invisible three-dimensional architecture, constantly shifting the pressure of air around you. A tuning fork provides a clear look at this energy. When you strike it, you inject kinetic energy directly into the room. As the metal prong snaps forward, it shoves nearby air molecules together, creating a dense cluster, a state of compression. A fraction of a second later, it pulls back. The molecules bounce into that empty space, creating a sparse region called a rarefaction. Individual air molecules shuffle back and forth in a fixed position, passing the momentum of the collision to the next particle. Like a crowded subway car suddenly hitting the brakes, the shockwave travels the length of the train, while the passengers stay in their spots. Human conversation is a rapid-fire chain reaction of microscopic atomic collisions, expanding outward from your mouth as a three-dimensional sphere of alternating pressure. Because this chain reaction relies on atoms colliding with other atoms, sound travels through any medium made of matter. While the vacuum of space is silent, a meteorite striking the moon would be audible to an astronaut standing a mile away. The longitudinal wave of the impact travels straight through the solid lunar crust, up their heavy boots, and through the suit to their ears. On Earth, this same mechanic operates on a planetary scale. Violent tectonic shifts create longitudinal, sound-like waves that plunge deep into the bedrock. Early geologists mapping these earthquake waves noticed a distinct pattern. As the vibrations traveled deep underground, the transverse waves hit a wall and stopped, while the longitudinal waves passed straight through the center of the planet and out the other side. Transverse waves cannot travel through the internal body of a liquid. By measuring the exact depth where those waves died out, scientists deduced that the Earth has a liquid core. Humanity mapped the molten center of our planet using the same atomic mechanics that carry a human voice across a room. Eventually, that expanding sphere of pressure reaches the human eardrum. By the time it arrives, the kinetic energy driving those molecules is remarkably weak. This chart shows the scale of that power. This large bar represents 250,000 microwatts, the energy of a dim bathroom nightlight. That barely visible sliver is the energy of a normal human conversation, just 1,000 microwatts. If human hearing processed energy linearly, the eardrum would be deaf to a dropping pin, or physically rupture the moment a thunderclap struck. Our hearing relies on ratios and multipliers. To perceive a single step up in volume, the physical energy of the sound wave must multiply tenfold. This logarithmic scaling allows us to navigate a world where whispers and thunderclaps represent two extremes of energy. It maps a massive physical range onto a usable, survivable scale. Once the sound wave pushes the eardrum and the brain decodes the signal, the remaining physical force must go somewhere. As the 3D sphere of the wave expands away from the source, it follows the inverse square law. Its finite energy stretches thinner across a massively multiplying surface area. With every microscopic atomic collision in the air, internal friction steals a tiny fraction of the wave's kinetic energy and converts it into heat. This resolves the coffee experiment. Screaming at a mug transfers a microscopic amount of kinetic friction directly into the liquid as thermal energy. All sounds ultimately meet the same end. The kinetic energy diffuses, fades into silence, and is absorbed by the surroundings, leaving the universe just a tiny fraction of a degree warmer than it was before.